In the vast darkness of space, 650 light-years from our world, a cosmic time bomb ticks toward its inevitable end. When this celestial giant finally detonates, it will unleash a cataclysmic wave of radiation and incandescent matter that will race across the Milky Way at unimaginable velocities, transforming everything in its path. Any planets unfortunate enough to lie within its immediate vicinity will be torn asunder, their rocky surfaces melted into rivers of magma, their protective atmospheres stripped away like gossamer veils in a cosmic hurricane. This ticking time bomb is close enough to Earth that on any clear night you can step outside, look up at the heavens, and spot it with nothing more than your naked eye. It shines as one of the most brilliant objects adorning our night sky, a stellar beacon that has captivated humanity for millennia. This is Betelgeuse, our nearest red supergiant star, and it stands on the precipice of one of the universe's most spectacular events, a supernova explosion. But the question that haunts astronomers and captivates our imagination is not whether this cosmic detonation will occur, but when. Will it happen in centuries, in years, or perhaps even in days? And when that moment finally arrives, what will it mean for us here on Earth, our fragile world suspended in the darkness? In pursuit of answers to these profound questions, scientists have turned their most powerful instruments toward this volatile stellar giant, studying it with unprecedented detail as it teeters on the edge of annihilation. They seek to unravel the complex physical processes and identify the telltale signs that will herald its imminent destruction. As Betelgeuse's cosmic timer inexorably counts down toward zero, this red giant continues to surprise us, revealing secrets that challenge our understanding of stellar evolution and the violent deaths of massive stars. Let us begin our journey into understanding Betelgeuse by examining the fundamentals of this remarkable star. Betelgeuse holds the distinction of being the 10th brightest star visible in Earth's night sky, positioned prominently as the left shoulder of the constellation Orion the Hunter, a star pattern that has guided travelers and inspired storytellers across countless generations and cultures. If you venture outside on a clear night and locate Orion in the winter sky, Betelgeuse reveals itself immediately as distinctly redder than its stellar neighbors, a color that speaks volumes about its nature and its fate. This crimson hue is not merely beautiful, it is a signature of the star's classification and its stage in the stellar life cycle. Betelgeuse belongs to a rare and fascinating category known as red supergiants, massive stars that have evolved far beyond the stable hydrogen-burning phase that characterizes stars like our Sun. Red supergiants dwarf our Sun in size, but Betelgeuse stands out even among these stellar behemoths. Its radius extends so far into space that if you were to place Betelgeuse at the center of our solar system, its outer layers would engulf Mercury, Venus, Earth, and even Mars, reaching beyond the red planet's orbit into the asteroid belt. To put this in perspective, Betelgeuse measures approximately 900 times the radius of our Sun, yet it contains only about 10 to 20 times the Sun's mass. This creates a remarkable situation where the star's matter is spread across such an enormous volume that its average density becomes extraordinarily low, far less dense than the air you breathe. The implications of this low density are profound. Betelgeuse's gravitational grip on its outer layers is tenuous at best, so weak that the star can barely prevent its atmosphere from escaping into the void of interstellar space. This feeble gravity, combined with intense convection currents rising from the star's nuclear furnace deep within, creates massive convection cells that roil across Betelgeuse's surface, gigantic bubbles of superheated plasma, each one large enough to swallow multiple planets whole. Computer simulations of these convection cells reveal a surface in constant turmoil, a churning ocean of incandescent gas where temperatures soar into the thousands of degrees. Imagine, for a moment, witnessing a sunset from a planet orbiting such a star. The sky would be filled with a crimson giant, its surface visibly bubbling and churning, covering a significant portion of the heavens above. Yet, as fascinating as Betelgeuse's current state may be, what truly captures our imagination and drives scientific inquiry is its impending demise. Supernovae within our galaxy are remarkably rare cosmic events. While astronomers detect hundreds of supernovae each year, these observations primarily occur in distant galaxies scattered across the observable universe, a testament not to the frequency of supernovae, but to the staggering number of galaxies in existence. Closer to home, within the confines of our own Milky Way galaxy, stellar explosions occur far less frequently. Current estimates suggest that our galaxy witnesses only 2 to 3 supernovae per century on average. This rarity means that the probability of a supernova occurring tomorrow remains quite low, but it is not impossible, and Betelgeuse stands as our most likely nearby candidate for such a spectacular event. When considering the potential impact of a stellar detonation like Betelgeuse's future supernova, proximity becomes the critical factor determining the consequences for nearby worlds. Interestingly, evidence suggests that Earth has experienced close encounters with supernovae before during its 4.5 billion-year existence. Our solar system currently resides within a region of space known as the local bubble, a relatively sparse cavity in the interstellar medium, spanning roughly 1,000 light-years across. Astrophysicists theorize that this bubble was carved out by the shockwave from a supernova explosion that occurred 10 to 20 million years ago, an event that Earth witnessed from a safe distance. More recently, scientists have uncovered evidence of another nearby supernova that detonated approximately 2.5 million years ago. The smoking gun for this event lies buried in Earth's geological record, a distinct layer containing elevated concentrations of iron 6-0 and manganese 5-3, isotopes commonly produced in supernova explosions and not naturally abundant on Earth. This supernova remained far enough away to avoid causing catastrophic damage to our planet's biosphere, but the evidence of its occurrence remains preserved in the rocks beneath our feet. However, not all cosmic encounters may have been so benign. Some researchers have proposed a controversial hypothesis, suggesting that the extinction of woolly mammoths approximately 13,000 years ago may have been triggered by a massive fragment of supernova debris impacting Earth. The proposed impact site contains magnetic spherules and traces of radioactive potassium-40, a substance found in supernova ejecta, potentially a smoking gun linking the extinction event to a cosmic catastrophe. Even earlier, woolly mammoth tusks dating back 34,000 years have been discovered bearing tiny impact craters caused by grains of slightly radioactive iron traveling at velocities approaching 10,000 kilometers per second. This speed matches perfectly with one of the characteristic velocities of supernova explosions, which typically range between 10,000 and 40,000 kilometers per second. One can only imagine the terror these ancient creatures must have experienced as debris from a distant stellar explosion rained down upon their world. To truly understand the scale of destruction a supernova can unleash, and to appreciate why proximity matters so profoundly, we must delve into the physics underlying these cosmic explosions. The universe offers two primary pathways through which stars can reach this explosive grand finale, though in each case, only certain types of stars qualify for this violent end. The first pathway produces what astronomers classify as Type Ia supernovae, typically involving a white dwarf star locked in a binary dance with a companion star. In these systems, the white dwarf gradually siphons matter from its neighboring star, slowly accumulating mass over millions of years until it reaches a critical threshold. The physics governing this process, while not fully understood, involves a delicate balance between two opposing forces: electron degeneracy pressure and gravity. In normal circumstances, the electrons surrounding atomic nuclei resist being compressed beyond certain limits, maintaining specific orbital distances and creating an outward pressure that counteracts gravitational collapse. A white dwarf represents matter compressed to extraordinary densities. A chunk of white dwarf material the size of a sugar cube would weigh as much as an automobile. Despite this incredible density, electron degeneracy pressure normally maintains equilibrium, preventing further collapse. However, in a binary system where the white dwarf continuously accretes matter from its companion, eventually gravity overwhelms this quantum mechanical resistance. When the white dwarf reaches approximately 1.4 times the mass of our Sun, a limit known as the Chandrasekhar limit, the entire stellar structure collapses catastrophically. Within seconds, carbon fusion ignites throughout the star, converting most of the white dwarf's mass into heavier elements and releasing an almost incomprehensible amount of energy as matter settles into its new, slightly more efficient nuclear configuration. The energy released in this process amounts to approximately 1/4 of a ronajoule. That's 1 followed by 45 zeros, all released within mere seconds. To provide context, this represents more energy than our Sun will emit over its entire 10 billion year lifetime. Naturally, no physical structure can contain such an energy release. The entire star explodes, ejecting its contents in all directions at approximately 6% of light speed, accompanied by an intense flood of gamma radiation that sweeps across the galaxy. The explosion's peak brightness reaches 5 billion times the luminosity of our Sun, a brilliance that persists for several weeks until the expanding debris cloud disperses enough that its overall energy density begins to dissipate. The second type of supernova, classified as Type 2, follows a similar catastrophic pattern, but involves a different stellar progenitor, and this is the type that will ultimately claim Betelgeuse. Type 2 supernovae require massive stars, at least 5 to 8 times more massive than the Sun, at the end of their evolutionary journey. Unlike the dead white dwarfs involved in Type Ia explosions, these massive stars remain active nuclear furnaces, still burning brightly when their moment of doom arrives. The balance maintaining these stars throughout most of their lives involves not just electron degeneracy pressure, but primarily the intense heat and radiation pressure generated by nuclear fusion in their cores. This fusion process converts hydrogen into helium, releasing tremendous energy that creates an outward pressure counteracting gravity's relentless inward pull. However, this equilibrium cannot last forever. Eventually, the hydrogen fuel in the stellar core becomes depleted, converted into helium ash, and the fusion process falters. Without fusion energy to maintain internal pressure, the core begins to compress under its own immense weight. Yet if the star possesses sufficient mass, this compression triggers a new phase of fusion. The rising temperatures and pressures in the contracting core become sufficient to ignite helium fusion, converting helium into heavier elements like carbon and oxygen. This cycle repeats multiple times for sufficiently massive stars, with each new fusion stage burning progressively heavier elements, carbon fusing into neon and magnesium, neon into oxygen and silicon, and finally silicon fusing into iron. With each successive fusion cycle, the star's internal pressure increases, causing the outer layers to expand dramatically until the star enters its red supergiant phase. Betelgeuse currently finds itself in this phase, likely fusing elements in concentric shells surrounding an iron core. But here lies the crucial limitation: iron occupies a special position in nuclear physics. Fusing iron into heavier elements does not release energy. Instead, it requires energy input. This means that once a massive star's core becomes dominated by iron, fusion can proceed no further. Without the energy production from fusion to generate outward pressure, the star's core can no longer resist gravitational collapse. What happens next occurs with terrifying speed. The iron core, no longer supported by fusion energy, collapses catastrophically in less than a second, compressing from a sphere roughly the size of Earth down to a ball perhaps 20 kilometers across. The infalling material rebounds off this incompressibly dense core, generating a shockwave that propagates outward through the star's layers. This shockwave, carrying unimaginable energy, blasts the star's outer layers into space at significant fractions of light speed. Meanwhile, the core itself may survive as an ultra-dense neutron star, or, if massive enough, collapse further into a black hole. Either way, the energy and material released by a Type 2 supernova rivals or exceeds that of Type Ia events, unleashing destruction on a scale difficult to comprehend. Given the immense power of supernova explosions, events capable of obliterating stars themselves, one might reasonably assume that any planet in the vicinity would have no hope of survival. This assumption holds true for planets in the immediate neighborhood of the exploding star. If our Sun somehow underwent a supernova explosion, which fortunately will never occur as it lacks sufficient mass, Earth would likely be partially or completely vaporized. The supernova's initial radiation burst would expose our planet's surface to temperatures 15 times hotter than the Sun's surface, causing rock itself to reach boiling point. Our world's rocky exterior would be whisked away into space during the weeks-long period of maximum supernova luminosity. However, what proves surprising is how rapidly this first wave of devastation dissipates with distance. Indeed, complete vaporization represents only one threat posed by supernovae, and not necessarily the most significant one. In 2011, experts from the University of Cambridge conducted calculations demonstrating that even planets orbiting at distances of 15 billion kilometers from their star, approximately 100 times the Earth-Sun distance, would remain physically intact during a supernova event. Rather than being vaporized, such planets would simply be ejected into interstellar space, sent flying outward now that their gravitational anchor had been destroyed. Of course, the fact that a planet's rocky crust might survive does not mean that life on that planet would persist. The problems facing any hypothetical ecosystem would be numerous and severe, even ignoring the blinding light of a supernova explosion, which would outshine entire galaxies and potentially cause permanent vision damage to any creature that observed it directly. The mere stripping away of a planet's atmosphere would create insurmountable challenges for complex life. High-energy radiation from the supernova, even if not directly lethal in the short term, would chemically alter the composition of any remaining atmosphere. Earth's protective ozone layer would be destroyed, vastly increasing radiation exposure at the surface. Ocean-dwelling phytoplankton, the foundation of marine food chains and producers of much of Earth's oxygen, would die in massive numbers. The consequences of this ecological collapse would cascade through food webs, triggering mass extinctions. Scientists estimate this kill zone extends to approximately 25 light-years from the supernova. Beyond this distance, the fury of the stellar explosion begins to diminish, as expanding shells of debris and radiation spread across ever larger volumes of space, diluting their energy density. Although the asteroid fragment that potentially killed woolly mammoths allegedly originated from a supernova 250 light-years distant, this would represent extraordinary bad luck if the hypothesis proves correct. Generally speaking, we would not notice significant damage from supernovae at such distances. Radiation levels would remain too low to trigger mass extinctions. By distances of 500 light-years, the effects become barely noticeable, perhaps manifesting only as an unusually bright new star visible in Earth's night sky for several weeks or months. This brings us to the obvious question that may have occurred to astute observers given that Betelgeuse lies roughly 650 light-years from Earth, well beyond even the 500 light-year threshold. Can we breathe easy, knowing that its eventual supernova poses no threat to our world? The answer, fortunately, is yes. You are not in any imminent danger from Betelgeuse. When this red giant finally explodes, the shockwave racing outward from the detonation will take considerable time to traverse the distance to our solar system. Even once it arrives, traveling at velocities of tens of thousands of kilometers per second, it will have spread across such a vast volume of space that its force will be negligible, less intense than the gentle push of the solar wind that continuously streams from our own Sunday. Neither Earth's magnetic field nor its atmosphere will be required to protect us. The Sun's heliosphere, the protective bubble of solar influence extending far beyond the planets, will be more than sufficient to deflect what little of Betelgeuse's supernova shockwave eventually reaches our neighborhood. No harm will befall Earth's biosphere, but the spectacle will be extraordinary nonetheless. Betelgeuse's supernova might shine as brightly as a full moon, making it easily visible even in broad daylight. Imagine seeing a brilliant new star blazing in the sky during your morning commute, a daytime star competing with the sun itself. Such an event would represent an unprecedented opportunity for astronomers and astrophysicists. Witnessing a supernova at such close range would reveal countless secrets about these poorly understood cosmic explosions, providing data that might take centuries of observations of distant supernovae to accumulate. Beyond the scientific value, the cultural and historical impact would be profound. Humanity would share a collective experience, watching together as a star that has shone in our skies throughout all of recorded history meets its spectacular end. This combination of safety and spectacle explains why so much interest surrounds Betelgeuse, with much of that fascination revolving around a single pressing question that dominates scientific conferences and public curiosity alike: when will it explode? Betelgeuse will detonate soon, though we must clarify what astronomers mean when they use the word soon in the context of stellar evolution. On astronomical timescales, where processes often unfold over millions or billions of years, soon translates to somewhere within the next 100,000 years, a time span that encompasses all of human civilization thousands of times over. However, some scientists working with specific models and assumptions predict that this red supergiant might detonate within considerably shorter timeframes, perhaps even within the next few decades. Their research operates under the assumption that Betelgeuse possesses a much larger radius than some previous estimates suggested, and if this proves accurate, it might indicate that the star has progressed further along its evolutionary path toward core collapse than we thought. This tantalizing possibility raises the prospect that our generation, or perhaps our children's generation, might witness one of the most spectacular astronomical events possible, a nearby supernova explosion visible to the naked eye for weeks or months. dominating our night skies and perhaps even visible during daylight hours. Yet Betelgeuse guards its secrets jealously, and over the last several decades, this enigmatic star has thrown numerous curveballs at astronomers attempting to predict its behavior. The inner workings of stars, especially red supergiants in their death throes, involve incredibly complex physical processes that remain incompletely understood despite decades of theoretical work and computer modeling. Betelgeuse dims and brightens according to several overlapping cycles, not all of which are fully explained by current models. The star exhibits a fundamental rhythm that likely relates directly to its evolutionary status and eventual detonation, as well as several overtone cycles, separate oscillation patterns that nevertheless connect to the underlying stellar structure. These cycles operate on timescales ranging anywhere from a few hundred days to 2170 days, approximately 6 years. Debate continues within the astronomical community about which cycle represents the fundamental mode and which constitute overtones or secondary effects. Because these cycles remain incompletely understood, Betelgeuse always seems to be doing something interesting that captures scientific attention and sometimes makes headlines. The star made news in 2009 when observations revealed it had contracted in size by approximately 15% over a period of just several years, a dramatic change for an object so massive. More recently, you may have heard reports that in late 2019 and early 2020, Betelgeuse underwent what came to be known as the Great Dimming, an unprecedented fading that sparked widespread speculation among both professional astronomers and amateur stargazers. Scientists initially found themselves puzzled by this dramatic change in brightness, and speculation ran rampant across social media and news outlets that this dimming might herald the imminent supernova explosion that everyone had been anticipating. Could this be it? Could humanity be about to witness the cosmic fireworks of a nearby stellar detonation? The anticipation was palpable. However, as is often the case in science, the truth proved more subtle than the dramatic interpretations initially suggested. New observations from the Hubble Space Telescope, combined with data from ground-based observatories, gradually revealed that the star itself had not actually dimmed significantly. Rather, a cloud of dust ejected by Betelgeuse had cooled and solidified between the star and Earth, partially obscuring our view, much like fog obscures a streetlight without the light itself growing dimmer. The sequence of events unfolded something like this. In September of 2019, Hubble detected heated material streaming away from Betelgeuse's atmosphere, moving outward at high velocities. Over subsequent months, this ejected material continued to expand and cool as it moved through space. By December of 2019, observers noticed that Betelgeuse had begun dimming substantially, with the southern hemisphere of the star appearing particularly affected. The current leading theory proposes that heated carbon compounds were carried along in the outflow of gas from Betelgeuse's surface. As this material moved away from the star and expanded into a larger volume, it cooled dramatically. Upon cooling, the carbon condensed into solid particles, essentially soot or dust, forming an obscuring cloud that passed across our line of sight to Betelgeuse. At the peak of the dimming event, Betelgeuse appeared approximately 2/3 fainter than its normal brightness, a dramatic change easily noticeable to experienced observers who regularly monitor the night sky. However, by April of 2020, Betelgeuse had returned to its normal brightness, indicating that the dust cloud had either moved out of our line of sight or dispersed completely into the surrounding space. While the Great Dimming did not herald an imminent supernova as some had hoped and predicted, the event sparked renewed intense interest in Betelgeuse throughout the astronomical community. This surge of attention and the allocation of precious telescope time to study the red giant led to an incredible discovery that had eluded astronomers for over a century. Betelgeuse might not be alone. For more than 100 years, since the early days of astrophysics, scientists had wondered whether Betelgeuse might actually belong to a binary star system, possessing a smaller companion star gravitationally bound to it and orbiting the massive red giant. Such an arrangement would not be unusual. Astronomers estimate that perhaps half or more of all stars exist in binary or multiple star systems, rather than shining alone like our Sunday. However, proving the existence of a companion to Betelgeuse presented formidable challenges. The red giant's surface behavior is so unstable and fluctuating with those enormous convection cells bubbling across its face and periodic pulsations changing its brightness. The being able to track the subtle, additional dimming and brightening patterns that would indicate a companion star's periodic passage proved almost impossible with available technology and observational techniques. However, the increased scrutiny following the Great Dimming of 2019 changed everything. Two independent research teams, working separately and using different approaches, found compelling evidence that Betelgeuse's longest brightness cycle, the one repeating every 2170 days, or approximately 6 years, could only be satisfactorily explained by Betelgeuse having a stellar companion. The breakthrough came not from trying to detect the companion directly by observing it passing in front of Betelgeuse, but rather from analyzing how Betelgeuse itself moves through space over time. The first team, based at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, and the second from the Center for Computational Astrophysics at the Flatiron Institute in New York, both examined decades worth of radial velocity data and positional measurements. These researchers noticed a tiny but detectable repeated variation in Betelgeuse's motion across the sky, as if the massive star were being gently pulled first to one side and then to the other by an unseen gravitational influence. This wobbling motion correlated perfectly with the 2170-day brightness cycle, suggesting strongly that a companion star orbiting Betelgeuse was responsible for both effects. Through careful analysis and modeling, both research teams independently concluded that this hypothetical companion, which quickly acquired the informal nickname Betelbuddy among astronomers and space enthusiasts, though its official designation is Alpha Orionis b, probably masses somewhere between 1/2 and 2 times the mass of our Sunday. The orbital calculations suggested it circles Betelgeuse at a distance somewhat less than that between our Sun and Saturn within the red giant's gravitational sphere of influence, but far enough away to avoid being engulfed by Betelgeuse's enormous extended atmosphere. Armed with this theoretical prediction, other astronomers sprang into action, attempting to obtain the ultimate confirmation, a direct image of this elusive companion star. Initial attempts using space-based telescopes proved unsuccessful. The extreme brightness contrast between Betelgeuse and its much fainter companion, combined with the limitations of available imaging technology, made direct detection impossible with those instruments. However, astronomers working with the ground-based Gemini North Telescope in Hawaii decided to try a different approach. The Gemini North facility boasts a primary mirror 8.1 meters in diameter, providing substantial light-gathering power and theoretical resolution, paired with a specialized high-resolution camera called a speckle imager, which compensates for the blurring effects of Earth's turbulent atmosphere by taking thousands of very short exposure photographs and combining them mathematically. The Gemini team pointed their powerful instrument toward Betelgeuse at a carefully calculated moment when the predicted companion star should be at its maximum angular separation from the red giant, the point in its orbit where it would Betelgeuse at a carefully calculated moment appear most distant from Betelgeuse, as seen from Earth's perspective. Their patience and timing paid off. Sure enough, the Gemini observations revealed something intriguing. A faint point of light separated from Betelgeuse by a tiny angular distance, visible only because the team had observed at precisely the right moment and used advanced imaging techniques to separate the companion's light from the overwhelming glare of its giant neighbor. Although the image remains somewhat blurred, being right at the limits of Gemini's resolution capabilities even with the speckle imaging technique, astronomers believe this represents our first actual photograph of Alpha Orionis b, affectionately known as Betelbuddy. The companion appears approximately 6 magnitudes fainter than Betelgeuse itself, meaning it emits roughly 250 times less light, making it extraordinarily difficult to detect against the red giant's brilliance. While this discovery does not constitute absolute 100% confirmation, multiple independent lines of evidence now point toward Betelgeuse having a companion. The radial velocity data, the positional wobbling, the correlation with the brightness cycle, and now direct imaging all tell the same story. Astronomers plan to observe again in 2027 when Betelbuddy should next reach maximum apparent separation from Betelgeuse, providing another opportunity to confirm the companion's existence and refine measurements of its orbital parameters. If confirmed definitively, the existence of Betelbuddy carries profound implications for understanding Betelgeuse itself. It helps astronomers rule out the 2170-day cycle as the fundamental pulsation mode, the underlying rhythm that might provide clues about when Betelgeuse will explode. Instead, that long cycle appears to be an orbital effect rather than something intrinsic to Betelgeuse's internal structure. This realization makes it more likely that Betelgeuse will take longer to detonate than the most optimistic predictions suggested. The star may not explode within our lifetimes after all, disappointing those hoping to witness this spectacular event, but presumably coming as a relief to Betelbuddy itself. The small companion star currently orbits well within what will become Betelgeuse's kill zone when the supernova occurs. When Betelgeuse finally detonates, Betelbuddy will be subjected to an onslaught of radiation and high-speed ejecta that will strip away its outer layers and potentially even trigger complex nuclear reactions in its atmosphere. The smaller star might survive as a runaway star, flung into space by the momentum transfer from the supernova blast. Traveling through the galaxy is a testament to its former companion's violent end. Predicting the moment of Betelgeuse's explosion remains an imprecise science, partly because much of what this remarkable star does continues to confuse and surprise astronomers. For example, measurements obtained using the Atacama Large Millimeter Array, or ALMA, have detected that Betelgeuse rotates at what seems like a mind-bending rate. Well, perhaps mind-bending requires some context to appreciate properly. The measurements indicate that Betelgeuse completes one full rotation approximately once every 20 years. On first hearing, this might sound underwhelming, even disappointingly slow. However, for a star with Betelgeuse's enormous size, this rotation rate translates to surface velocities reaching 18,000 kilometers per hour, or approximately 5 kilometers per second. To provide perspective, this is roughly 10 times faster than Earth's surface velocity due to our planet's rotation. And for a star of Betelgeuse's immense scale, such rapid rotation essentially defies the laws of physics as we understand them. How can this be? Understanding why Betelgeuse's rotation appears so problematic requires exploring the ways astronomers measure stellar rotation and the physical principles governing spinning celestial objects. When dealing with relatively nearby objects in our solar system that possess substantial angular size objects like the sun, moon, or planets, determining rotation rates is straightforward. You simply point a telescope at the object and watch its surface features move in real time, tracking how long it takes for a particular feature to rotate around and return to its starting position. The moon, for reference, subtends an angular diameter of about half a degree as seen from Earth, making its features easily visible even to the naked eye under good conditions. Jupiter, despite being vastly more distant, still presents an angular diameter of approximately 1/100th of a degree, yet its features remain clearly visible through even modest telescopes, allowing amateur astronomers to track its rotation period of roughly 10 hours. So what about Betelgeuse, a star hundreds of times larger than our Sun? Despite its enormous physical size, Betelgeuse lies far enough from Earth that its angular diameter measures merely 43 milliarc seconds, approximately 1,000th the angular size of Jupiter. This makes the star appear as essentially a blur even through the most powerful telescopes available. Fortunately, astronomers possess another ingenious technique for determining whether stars like Betelgeuse are rotating, a method that does not require directly resolving surface features. This approach relies on the Doppler effect, the same phenomenon responsible for the familiar change in pitch of a siren as an ambulance speeds past. When the ambulance approaches you, sound waves from its siren reach your ears at higher frequency than if the vehicle were stationary, making the siren sound higher pitched. As soon as the ambulance passes and begins moving away, the effect reverses. Sound waves arrive at lower frequency, and the pitch drops noticeably. What you probably have not noticed is that the Doppler effect applies equally to light waves reflecting off the ambulance, just as it affects sound waves emanating from the siren. The higher frequency light as the ambulance approaches shifts slightly toward the blue end of the spectrum, while the lower frequency light as it recedes shifts toward the red end. The reason this visual effect escapes notice in everyday life is simply that light travels approximately 1 million times faster than sound. An ambulance would need to reach utterly impossible velocities, significant fractions of light speed, before the optical Doppler shift became noticeable to human eyes. However, while we lack ambulances moving at 5 kilometers per second here on Earth, such velocities are commonplace in the cosmos, making optical Doppler shifts readily measurable with appropriate instruments. This brings us back to Betelgeuse and the problem of measuring its rotation. When a spherical star rotates, half of its surface inevitably moves toward Earth, while simultaneously the other half moves away. This creates a gradient of Doppler-shifted light across the star's visible disk. Even if the star appears too small and blurry for astronomers to distinguish any surface features, by carefully analyzing the spectrum of light received from the star, they can detect which side appears slightly bluer, indicating motion toward us, and which side appears slightly redder, indicating motion away from us. The magnitude of this color shift, the difference between the bluest and reddest light received, allows astronomers to calculate the star's rotational velocity with considerable precision. This represents the technique that astronomers employed when analyzing data collected by ALMA, ultimately concluding that Betelgeuse's surface moves at approximately 5 kilometers per second due to rotation. This conclusion would be perfectly acceptable, except for one significant problem. The known physics of stellar rotation predicts that 5 kilometers per second is impossibly large for a red supergiant of Betelgeuse's size and mass. Our Sun provides a useful comparison point. The Sun's equatorial rotation velocity measures approximately 2 kilometers per second, and our star is roughly 1,000 times smaller in radius than Betelgeuse, while being about 10 to 20 times less massive. Now imagine that the Sun somehow expanded to match Betelgeuse's size, swelling until it engulfed the inner solar system and nearly reached Jupiter's orbit. To conserve angular momentum, a fundamental physical quantity that remains constant unless external forces act on a system, the Sun's rotation velocity would need to decrease dramatically as its radius increased, following the principle that makes spinning figure skaters slow down when they extend their arms outward. Specifically, if the Sun expanded to Betelgeuse's radius, its rotational velocity would drop to merely 2 meters per second, 1,000 times slower than its current rotation. Furthermore, if this enlarged Sun also gained mass to match Betelgeuse's 10 to 20 solar masses, the rotation would slow even further, perhaps to around 20 centimeters per second. The general principle is clear: larger, more massive stars should spin more slowly than smaller, lighter ones. Yet, Betelgeuse appears to defy these expectations completely, rotating at speeds far exceeding theoretical predictions. What could explain this discrepancy? One compelling possibility involves a process colorfully termed stellar cannibalism. Despite the dramatic name, stellar cannibalism simply describes what occurs when one star gravitationally strips material from a companion star, gradually consuming its neighbor over millions of years. Typically, this happens in close binary systems, where a more massive or more evolved star pulls gas layer by layer from its companion's outer envelope until only the stripped core remains. This accreted gas carries angular momentum from the donor star, so the accreting star ends up not only growing larger, but also spinning faster than nature would normally permit for a star of its new size and mass. Could this represent the true story of how Betelgeuse acquired its apparently impossible rotation? Perhaps Betelgeuse once had a closer companion than Betelbuddy, a star that spiraled inward over time, until Betelgeuse's gravity began tearing it apart, consuming its mass and angular momentum before the companion's remnant either merged completely with Betelgeuse or was ejected from the system. This scenario would neatly explain the rapid rotation while also accounting for other peculiarities in Betelgeuse's behavior and composition. However, a team of researchers collaborating across institutions in Europe and China recently proposed a radically different explanation. Perhaps Betelgeuse's apparently ludicrous rotation is nothing more than an elaborate optical illusion, a misinterpretation of data caused by the star's chaotic surface activity. To understand how this alternative explanation works, we must reconsider exactly what the ALMA observations measured. Although ALMA's images of Betelgeuse show substantial detail for such a distant object, they remain far from crystal-clear photographs. The observations revealed that one hemisphere of the star emits light shifted slightly toward redder frequencies than average, while the opposite hemisphere emits light shifted slightly toward bluer frequencies. The straightforward, obvious interpretation of this 50-50 split in color is rotation one half of the star moving away from Earth while the other half moves toward us. But what if rotation is not the only phenomenon capable of producing such a pattern? Computer simulations of Betelgeuse's surface dynamics reveal an environment of unimaginable violence and chaos, with the star's outer layers constantly churning under the influence of powerful convection currents rising from deep within. These simulations show the surface as a seething cauldron, constantly bubbling like water approaching boiling point in a pot, except the scale and energy involved dwarf any terrestrial comparison. Each convective bubble on Betelgeuse's surface measures approximately 100 million kilometers across, large enough to engulf multiple planets the size of Earth. These bubbles propagate outward at velocities up to 30 kilometers per second, carrying enormous amounts of energy and momentum. Even today's most advanced spacecraft technology would prove utterly inadequate to escape such a bubble. If one were headed in your direction, your only hope for survival would be for the bubble to reach the top of its trajectory and collapse violently back down onto the stellar surface before reaching your position. As countless gas bubbles across Betelgeuse continually rise and fall, the star's surface becomes a complex mosaic of regions moving either toward or away from distant observers on Earth at any given moment. The Doppler effect causes light from rising regions to appear blue-shifted, while light from falling regions appears red-shifted. The international research team proposing this alternative explanation argued in their recent paper that Betelgeuse might not be rotating rapidly at all. Instead, the ALMA observations might be detecting the range of light frequencies produced by turbulent convection across the star's surface rather than rotation. Astronomers may have been inadvertently misinterpreting these Doppler shifts as rotational effects when in fact they represent the chaotic up and down motions of convective cells. However, a careful observer might notice an apparent problem with this alternative explanation. A rotating star should produce a smooth, continuous gradient of Doppler-shifted light, transitioning gradually from maximum blue shift on one limb through zero shift at the center to maximum red shift on the opposite limb. In contrast, a turbulent star should produce a random, patchy distribution of colors, with blue-shifted patches wherever bubbles happen to be rising, and red-shifted patches wherever material happens to be falling back down. These two patterns seem fundamentally different. How could astronomers using ALMA possibly mistake one for the other? If observers detected a smooth color gradient, should not the patchwork convection explanation already be ruled out? In an ideal world with perfect observational data, yes, the distinction would be clear and unambiguous. But Betelgeuse lies so distant from Earth that even ALMA's impressive resolution cannot produce truly detailed images of the star's surface. The observations amount to blurred impressions rather than high-definition photographs. When the research team ran detailed simulations of Betelgeuse's convective surface and then artificially blurred those simulations to match ALMA's limited resolution, something remarkable emerged. The simulations predicted that the random, bubbly patchwork of red-shifted and blue-shifted regions would be easily mistaken for a smooth rotational gradient, approximately 90% of the time once observational blurring was taken into account. This finding suggests that even if the ALMA astronomers conducted their analysis perfectly without making any errors, they may have been deceived by Betelgeuse's boiling surface into concluding the star spins far faster than it actually does. The turbulent convection, when viewed through instruments with limited resolution, naturally produces patterns that mimic the signature of rapid rotation. This means astronomers now find themselves chasing a critical objective, obtaining higher resolution observations of Betelgeuse that could more accurately distinguish between these two competing scenarios. Can improved data definitively tell us whether we are seeing true rotation or an illusion created by convection? The encouraging news is that better images of Betelgeuse already exist in telescope archives, captured using ALMA with longer exposure times and different observational configurations. The less encouraging news for those of us eagerly awaiting answers is that properly analyzing these data will likely require several more years of painstaking work. Those answers are coming, though, carried forward by the dedicated efforts of astronomers determined to unravel Betelgeuse's mysteries. For now, the question remains open to speculation and scientific debate. Is Betelgeuse genuinely spinning at 5 kilometers per second after having consumed a companion star millions of years ago? Or will the newer claim that this rotation speed represents nothing more than an optical illusion ultimately be vindicated when higher resolution data are analyzed? Only time and careful analysis will provide the definitive answer. So there you have it, a comprehensive journey through everything we currently know about Betelgeuse, a star balanced on the knife edge of cataclysm, counting down the final moments before its spectacular demise. It is little wonder that we regard such a savage, violent event with fascination bordering on obsession. Humanity has always held a deep appreciation for explosions, as evidenced by virtually every culture's enthusiastic embrace of seasonal fireworks, displays, and pyrotechnic celebrations. So whenever it finally occurs, whether in our lifetimes or millennia hence, a supernova detonation that illuminates our night sky will be an awe-inspiring spectacle to behold, a cosmic fireworks display on a scale that dwarfs anything humanity could create. Though we can rest easy knowing that in Betelgeuse's case, we will experience this grand finale from a very safe distance, protected by the vast gulf of space that separates our world from this doomed star. The universe offers few guarantees, but we can be confident that when Betelgeuse's time comes, Earth and its inhabitants will have front-row seats to one of nature's most magnificent performances, safely shielded from harm yet perfectly positioned to witness a phenomenon that occurs only a handful of times per century in our galaxy. This cosmic drama continues to unfold in the heavens above, whether we watch or not, indifferent to human timescales and concerns, following the inexorable laws of physics toward an ending written in the stars since Betelgeuse first ignited its nuclear furnace millions of years ago. We remain fortunate witnesses to this unfolding story, able to study and appreciate the intricate processes driving this red giant toward its ultimate fate, gaining insights that illuminate not only Betelgeuse's individual destiny, but the broader story of how stars live and die throughout the cosmos.